Well, so this is the first class on this applied nuclear physics essentially course. And well, we have to start by making two essential questions, right? What is nuclear physics and what is it good for? Because, well, that's why we're here, right? Nuclear physics. Essentially, nuclear physics is, well, the physics applied to the atomic nucleus. So it has to do with anything about the nucleus, meaning it's the physics of things that keep the nucleus together. It's the physics of things that make the nucleus change in time, so essentially decay or something. And it's the physics of things that interact with the nucleus, right? And why are we doing this? What is it good for? Why do we want to study this? Well, first answer, right? We're scientists. Curiosity always plays a part here. But no, we all know about, I don't know, nuclear energy, nuclear weapons. Shouldn't exist, but they do. What can we do? Uh, and there's also nuclear medicine. But as I want to show you through this course, and especially on the last class, there's much, much more than that, right? Essentially, nuclear physics and the interaction of nuclear radiation and matter, they have to do with the way we pack things, the way we preserve things, the way we analyze things. So that's the idea. And of course, that's the fact that if done in not in a proper way, exposure to radiation can be bad for you. So all of this we want to somehow take into account during this course. So let's just dive down a bit through history. So I think we all know the story of the atom, but let's go. On five centuries before Christ, there was Democritus and others, that philosophers that thought, okay, there should be something that's the smallest part of matter. You can divide matter indefinitely. No, there was two ways of thinking. Some people said, okay, we can, and some people said, no, there's a limit. There's the smallest part we can. And so they gave this name that in atomo, which in Greek means no division. Okay, but let's make one thing clear. They had no idea about chemical elements and anything. For them, the atom was, I don't know, one atom of my cell phone. That's the smallest atom of my cell phone, or of me, or you, or whatever, right? So there was the atom of a chair, which was different than the atom of a telephone. I don't know. Then, in the beginning of the 19th century, chemical elements were discovered, and they didn't relate that to atoms at all. They knew there was something they understood as chemical elements, and then John Dalton said, "Okay, we that concept of the atom is perfect here. We have an atom, but it's different for each chemical element. We have an atom for hydrogen, one atom for helium, and well, that's the beginning. Just a fun fact here: John Dalton, yeah, this guy who thought, clever guy who thought of the atoms in a modern way. Well, his name is not just. You may have heard of Daltonism, people that see colors wrongly. Yeah, John Dalton is the reason for that name because he was Daltonic himself, right? And so he thought his eyes had some problem, and in the end, he decided to donate, after his death, donate his eyes to science because he was sure His eyes were filled with some colored fluid. Not the case. Now we know it's just a matter of recipient, light recipients in the eye. But okay, fun fact: John Dalton is the original Daltonic. So okay, now we have atoms. But what are those atoms? We don't know. We only know they're small. And then in 1895, Röntgen was studying cathode ray tubes, and he accidentally discovered X-rays. Right? There's a story here too. He thought was crazy. Things didn't make sense. It was probably the work of the devil, and so he locked himself up. But anyway, he did what scientists do, which is, okay, let's repeat this in several controlled ways, and he understood, okay, there's something here I don't understand, but it can cross my meat, but not my bones. It can cross my meat, but not my rings and other things, right? And he discovered the X-rays. No idea what they were. In the next year, Henri Becquerel, he found out, okay, there's some atoms that emit something very similar to these X-rays, but we don't need to plug them on power outlet or something. They just emit it. And 1 year later, J.J. Thomson discovered the electron. So you see, after 90 years trying to understand the atom, all of a sudden things started to happen. And they didn't start to happen just by chance. The fact is, just prior to that, electricity was discovered and understood. So until 1890s, we had our eyes to see the world. Well, Galileo discovered or created the telescope so we could use better our eyes, but it was only our eyes. Visible light was the tool we had to understand nature. And all of a sudden, now we had electricity to understand nature. And by using electricity, we discovered several things that were hidden because they didn't have anything to do with visible light, right? So, okay, now we have electricity, and we know there's an electron, and we know there's X-rays and radioactivity. In 1904, J.J. Thomson proposed what was called the plum pudding model. So the atom was a big thing with small electrons plugged into it. And it was okay, we had a positive thing that was big here, big in this case, right? And several things encrusted with, like, plum, like here we would say raisin on a bread. You have the raisins and you have the bread. But okay, 2 years later, Rutherford was playing with something called, he knew alpha radiation, and he started to throw alpha radiation over a gold foil. And well, if this was right, this model would have these big balls here all placed. We would have soft scattering, right? Imagine you have big balls here, you have small things you throw in here. They would scatter right most any direction, and just a few would cross this barrier. What he discovered was exactly the opposite. Most of the radiation, the alpha radiation, just passed through the gold foil, which was impossible to explain with using this model. And some of the alpha particles, they were backscattered. I mean, they just collided and came right back. So this is impossible with something soft like this. So he thought, okay, something is not right with this model, and after 3 years working things out, he came up, okay, so the nucleus must be very small, 10,000 times smaller, or 100,000 times smaller than the atom itself, so that most of the atoms the alpha particles will go through it with no problem, and just a few of these will collide and it does this as a compact, small thing, there's a big probability it will backscatter, right? So the nucleus must be very compact, just 100,000 times smaller than the atom itself, and the rest of the atom is just made by empty space with electrons crossing it. So we have some idea of the atom, and then there came the quantum mechanics. And okay, quantum mechanics posed some troubles to this model, and Niels Bohr, which was one of the founders of quantum mechanics, said, okay, there are solutions to our quantum equations which are stable, meaning the particle can orbit the nucleus without emitting radiation, because usually if you have a change of direction you should have emission of radiation. Quantum mechanics said no, there are orbits that are stable, and so this is the modern atom we know, right? So we have stable orbits for the electrons, and the emission of absorption of radiation, in case X-rays, just corresponds to electron changing orbit, right? And the quanta of energy is emitted. And the electron angular momentum should be an integer of h over 2 pi. So, okay, but we now know there's positive nucleus here and electrons, but what is this positive nucleus? And then we're coming to what we need to understand for this course, right? And so in 1919, Rutherford discovered the proton. And okay, the proton had a positive charge, and okay, this is the nucleus. But there was a problem with it. If you thought, okay, hydrogen, we have one proton, one electron, and it goes well. So they already knew that helium had 2 electrons, so it should be the nucleus had positive 2 charge. But when they did the experiments, they found out that the helium nucleus, its weight was 4 times the weight of hydrogen. But wait, how can it be? Because if hydrogen is 1 proton, helium should be 2 protons, should have twice the weight, not 4 times the weight. And then they came with an ingenious solution. No, we have 4 protons and 2 electrons inside the nucleus. So okay, now we have charges plus 2, because 2 electrons, they just cancel out the charges of 2 protons, and we're good. No, it happens that if you apply quantum mechanics rules in this problem, you cannot have, because of what they call the uncertainty principle, which is part of the basis of quantum mechanics, you cannot have electrons, particles as light as an electron could not be restricted to space as small as the nucleus unless their energy was very, very high, and then they wouldn't be bound to the nucleus after all. So no, having 4 protons and 2 electrons on the nucleus was not a solution. Then most of the people thought, okay, we must have a proton with no charge, a neutral particle that's like the proton but has no charge. And indeed they thought of it, they proposed it, but they said, okay, this will be very tricky to measure. Why? Because everything they were doing was studying things with electrical probes. So you would do, you have radiation, you just put 2 plates here, put voltage difference, and the radiation will go one way or the other. You say, okay, this is a charged particle, negative particle or something. If it's neutral, it doesn't react to this, so nothing to do. And so it was that it took 13 years for someone to finally say, okay, I've seen a neutron. This guy was James Chadwick. He was a student of Rutherford, and what he did in fact was he performed several experiments with several things, and all of a sudden he noticed that if you used alpha radiation, if you had something and you have an alpha decaying particle, a decaying nucleus, for instance uranium or something, and you have a beryllium cover, all of a sudden you notice there's radiation there which couldn't correspond to any of the known radiations, and it was definitely neutral. So he said, okay, we found a neutron. And so in 1932 we had the definitive atomic model. So you have a compact nucleus made by protons and neutrons, no electrons on the nucleus, and you have electrons that occupy the quantum orbital. So essentially the atom is empty, almost empty, with a very, very small nucleus in the middle with protons and neutrons, and all these empty spaces you have electrons traveling through it. Perfect. So this is what not really the Bohr nucleus, it's more, but it's a very good approximation. So you have nucleus and the electrons, and it must be noticed that while the nucleus is 10 to the minus 15, so it's a femtometer, the atom itself is almost 100,000 times larger. And that's an important thing, because this number will come back in a moment, right? So if you think, now just going a step further, I said, okay, it's not really this model, it's not really orbits like this. No, when you solve the quantum equations, you don't come to linear orbits, but rather to surfaces. And so just to have you an idea, the s orbital is just like a sphere. The p orbital is just like two pills. D orbital is like some droplets. And it goes like this, right? Just to have you an idea of what orbitals are about. So okay, let's talk about the nucleus now. The nucleus, so as I said, it's made of protons and neutrons. And there's a general term we use for both these particles. They are nucleons, meaning they are the kinds of particles you find in a nucleus. So protons and neutrons are both different flavors of nucleons, right? And they are kept together by the strong nuclear interaction. Right, we'll talk about this in a minute, but there's four essential forces, and the one that plays a part here on the nucleus is the strong nuclear interaction, which is attractive to very small. It has a very short range and is attractive until a certain point, and then it's repulsive in a very, very close range. And so that's it, that's the nucleus. And the proton mass we have here in kilograms and the neutron mass, they are very, very similar. You see the difference is on the third digit. The main difference being the proton has the same charge as an electron, but in opposite sign, so it's positive, and the neutron has no charge. So that's the atom. If we think we have very small nucleons, we have a nucleus that's very small too, and a much, much larger thing we call the atom. You may have heard of those comparisons, right? If the nucleus was a pin, the atom would be the size of a football field or something. That's roughly something like that. And so we're talking about the nucleus. Let's think of comparison first. We all know something about chemistry, which has to do with interactions between atoms, or more precisely between electrospheres, between the electrons that are in each. And so let's compare nuclear physics with the nucleus. As I said, okay, the nucleus is 10,000 times, 100,000 times smaller than the atom, right? There's a trade-off to this. When we're talking much smaller, we're talking much higher energy required to keep things together. And so, while in chemistry we have electron volt, energies are around an electron volt, here in the nucleus we have energies that are 100,000 to a million times greater than this. Just as a side note, and this is an important thing here, the electron volt is a unit we use for atomic and nuclear structures for one reason. It's an energy unit, but if we talk about joules, we're talking about, we have something like 10 to the minus 19 joules would be a typical interaction in chemistry. And well, we would do better not having to carry this 10 to the minus 19 everywhere, right? So we use a unit called electron volt, which is essentially the electrical potential energy on the charge of one electron exposed to a 1 volt voltage, right? Potential difference. So this is essentially what happened. This is essentially what an electron is exposed to in the outer orbits of an atom. So okay, this is a very convenient unit. So all you need to know, you don't need to know how to convert it to joules. You can do this later. But the important thing is to understand that electron volt is a unit of energy, right? So in the nucleus we have almost 1 million times more energy, right? And that's what made people start to think, okay, we should use this to release energy, right? And then you think quickly on electrical power and you think of explosives. And well, in chemistry you have chemical reactions, which are when atoms interact with one another and exchange electrons. In nuclear physics we do have nuclear reactions, which are when nuclei interact with each other and exchange nucleons. Not the best definition, we talk about nuclear reactions later, but that's the idea. And in chemistry, everything is mediated by the electromagnetic interaction. So it's electrons interacting with electrons, essentially charge interacting with charge. In nuclear physics, we have the strong interaction, so it's particles interacting with other particles, regardless of the electromagnetic interaction. Not really regardless, but the nuclear interaction is much, much stronger. So the unit we'll be using a lot here is the electron volt and its multiples, right? So you have the kilo electron volt is 1000 electron volts, mega electron volt is 1 million electron volts, and so on. Just to give you an idea, to remove 1 electron from a hydrogen atoms, you need 13 electron volts. So you have one hydrogen atom, I want to remove the electron, I have to give it 13 electron volts. To separate a neutron from a proton in the heavy hydrogen nucleus, so you have a nucleus that's essentially just a neutron and a proton, you would need 2.2 mega electron volts, or 163,000 times more. As you see, that 100,000 times effect comes up here quickly. So, first question, what is a nuclide? We have to define some things before we can go on. So we define something called nuclide. Nuclide is something that has a certain number of protons, a certain number of neutrons, right? So you have a nuclide which has Z protons and N neutrons. Z, the number of protons, defines the chemical species of the nuclide. Why? Because let's remember that what really gives the chemical characteristics of an atom are the electrons, right? The electrons in chemical interactions, it's only the electrons that play something. And the electrons, they don't see the neutrons because the neutrons, they have no charge. They only sense charge. So the atomic number is the number of protons or the number of charges in the nucleus, and so this gives all the chemical properties of the atom. The number of neutrons define what we call isotope. Talk about that in a minute. So you have a number of protons, but you may have different numbers of neutrons, and this will define different nuclides of the same chemical species. And well, as we shown before, protons and neutrons have very similar masses, so a very good approximation of the overall weight of that nucleus would be just to add up number of neutrons and number of protons, giving something we call atomic mass. So it's the sum of protons and neutrons. So if I have 6 protons and 6 neutrons, I have atomic mass of 12. And a nuclide is essentially each specific combination of A and Z. Right, in that case I said, okay, 6 protons, 6 neutrons, giving a mass of 12. 6 protons means carbon, and so, as I said, see, number of protons define the chemical species. So 6 protons means carbon, and number of mass in this case, 6 plus 6 is 12, so we have carbon 12, right? Oxygen 16, you have 8 protons, 8 neutrons, mass is 8 plus 8, 16. These are different nuclides. And nuclides can rather either be stable or unstable, which means they are radioactive. And then we call them radionuclides. And what's the representation? Essential representation is this. We have a chemical symbol here. On the top left, we have the mass number, which is the total number of nucleons there, right? And down on the left, we have the number of atomic number. So, as I said, another example we have, for instance, maybe you've heard of carbon 14, which they do for defining aging, for aging things, to know the age of some fossil or something. What's that? Carbon 14. So you have you know it's carbon, you know it's 6 protons, right? So this number is not needed. We put it here usually for convenience. So it has 6 protons, meaning it's carbon, and the mass is 14. If you do 14 minus 6, you say, okay, it has 8 neutrons. Unlike the carbon 12, I said, that had 6 neutrons, right? So that's it. That's the symbol. And it's important to notice that the mass number should be up on the left. On ancient books from the 60s or something, you will find sometimes the number of mass on the top right. It shouldn't be used like this. It was a notation that was used until the 70s and was defined because there was no real definition of what should be, and then there was an international agreement between UPAC, which is the International Union of Chemists, and UPOP, International Unit of Physicists, that said no, it should be on the right, top left, not right? So, yet you will see some texts, and even in these classes there will be places, and I'll point them out for you, where this number of mass is here. It should never be here. It should always be where it is here, right? And so, okay, now let's say I talked about carbon 12 and I talked about carbon 14. Both are carbon, right? But they're not the same thing. And that's what we call isotopes. Isotopes are nuclides that belong to the same chemical species, meaning they have the same number of protons, meaning they have the same electronic characteristics. So they are both chemically identical, but they have different mass, which means their nuclear behavior is completely different. So much different, in fact, that if you take hydrogen, light hydrogen is just a proton, so it has mass 1, charge 1, right? It's the most common element in the universe, most common nuclide in the universe. Then we have deuterium, which is known as heavy hydrogen, which has 1 proton and 1 neutron. So mass is 2, but still 1 atomic number. It's stable, it's just heavier, right? And then there's also in nature something called tritium, which is a radioactive hydrogen. It has 2 neutrons and 1 proton. If you take a look, this is still hydrogen, much heavier than the first one. So chemically, still hydrogen. But if you take a look, it is radioactive. So you see, we have all of these are hydrogen, but this one is radioactive. The others aren't. And this doesn't mean either that these two are identical. They're not. That's why you sometimes listen, and we talk about this later in the course, why there's nuclear reactors that use heavy water. Heavy water is water where hydrogen was traded for this heavy hydrogen, right? Because they're not nuclearly, they are the same chemical element, but their nuclear behavior is completely different. Okay? So, another thing. So I said there's isotopes of hydrogen, and the 3 occur in nature. And there's also, as I pointed before, carbon has some isotopes too. And how does it go? Isotopes are found in nature in approximately constant ratios. The differences are minimal. There's people who study these differences and try to use this as a signature to things. But but essentially it's very broadly the same. Let's take uranium, for instance. We have 3 isotopes you find in nature. There's uranium has 92 protons, right? So there's uranium-234. It has 142 neutrons. This is found in nature in a very negligible amount. We'll talk later, it's related to the existence of uranium-238. There's uranium-235, which has 1 neutron more than 234. It's very, you've probably heard of it. It's the kind of uranium you would use in nuclear reactors, explosives, and so on. This is 0.7%, meaning in 1,000, if you get 1,000 uranium atoms, 7 will be uranium-235. 1993, so 99.3% of these atoms, uranium atoms, will be uranium-238, which has 146 neutrons, right? And this should be true. In Brazil, it should be true. In Nigeria, it should be true. In Korea, or in the bottom of the ocean, it's essentially the same. The differences we might find are in a smaller scale than this, better than 0.1%, right? So, then we have what we call isotopic abundance, right? That's it. The isotopic abundance of 238 uranium is 99.3%, of 235.7%. And then if we just do some calculation, let's take silicon. Silicon exists in nature in 3 natural forms: silicon 28, 29, and 30, and these are the isotopic abundances. Each nuclide has its own mass, if you calculate, right? So this is the one for silicon 28, this is the one for silicon 29, and this is this one for silicon 30. And I'll define these units later. Just think of it as units, right? It's what in chemistry in school we learn as atomic mass unit. And so, what is the chemical mass of silicon? The one you'll find in the tables and uh, everywhere. You just do a weighted average of all this. So you have the abundance of silicon 28 is 0.923, right? 92.23% times this. And then you have 4.767% times this mass, 3.09% times this mass, and you get 28.083 units. This is the atomic mass of silicon, right? If you have a general sample of silicon, it's composed by these three isotopes in these proportions, and so the mass is this one, right? Just take each mass and multiply by the percentage, and you get the elemental mass. Now, there's another thing we sometimes have to care about, which are isomers. Isomers are a funnier thing because they have the same number of protons and the same number of neutrons, meaning they are exactly the same nuclide, right? Because it's carbon 12, it's still carbon 12, whatever. But they are in a different energy state, meaning that, for instance, let's get technetium 99, right? This is what we call the fundamental state, which is the lowest energy state. But there's one excited state, which has something of a half-life, and it's the same atom, it's the same nuclide, but this one is different because this one is in an excited state, so it has to decay from this excited state before becoming this one, right? So the same nuclide in a different energy state. So if we define the fundamental state as the lowest energy state possible, then we have these excited states, which can be, if you have a very short half-life for these isomer, things like 1 microsecond or slower, or faster, I mean, we call it just an excited state. But there are excited states which are much larger half-life, right? And we call them metastable. And then we get this M here. M stands for metastable. In this case, for instance, this guy here has 6 hours half-life. So, just going back to our comparison, this is the chemical table, periodic table as proposed by, just forgot his name, but whatever. So here you have all the elements, and yeah, this is not up to date because all this line is full now and these guys here have names, but it doesn't matter. So each place in this chemical table is an atom, and you have the properties of these atoms, right? Like their electron affinity and everything. But when we talk nuclear physics, as I told you, the same element can have several isotopes, which are nuclearly completely different. So when we talk about nuclear physics, we need a table like this, which, as you see, has much, much more dots than the regular periodic table. Each small square here is one nuclide. And just to put things into perspective, you see this very thin black line here. We have all these elements in black here, these nuclides in black, are the ones that are stable, are the ones that really make up everything you know. Everything except these small ones is radioactive, right? So you see that just a very small minority of the atoms we know in the universe are stable, right? Another thing you should notice here is on very light nuclei, you have essentially a 1-for-1. The stable nuclei have the same number of protons and neutrons. So, but you see these bands here, right? If you have a line here, you see definitely goes from this behavior to, in heavier atoms, it tends to have much more neutrons. That's why that happens. If you think, protons have positive charge, right? Although the nuclear interaction is much, much stronger than the electromagnetic repulsion between positive particles, when you start to pile up too many protons, the repulsion starts to play a part. And you can think of the neutrons as the glue that keeps protons together. So if you have more and more protons, every time you need more neutrons and more neutrons and more neutrons to keep this from falling apart. And that's why for heavier nuclei right here would be 90 per 90, and you have much more than 90, you have 130 neutrons. Why is that? Because you need much more glue to keep all that positive charge from just blowing things apart. Right, so light nuclei you essentially have for the stable nuclides, like in carbon 12, 6 protons, 6 neutrons. Oxygen 18, 8 protons, 8 neutrons. Nitrogen 14, 7 protons, 7 neutrons, and it's all good. When we go all the way down there, we have uranium 238, which has 92 protons and 136 neutrons. So you see much more neutrons and protons to keep that beast together. And so this is the nuclear table, just taking a very close here. So you see each dot now is a different nuclide, which is its nuclear characteristics, right? Like the abundance, which in the black ones you see the abundance here. Here, for instance, in fluorine, you only have one stable, so it's 100% of this. And you have the half-lives, so fluorine 18, it's almost 2 hours. Fluoride 17 is essentially 1 minute, and so on, right? Oxygen, we have 3 stable isotopes, but we have several other isotopes with shorter or longer half-life depending on the isotope, right? So, and then we have many other characteristics here, like the radiations they emit and nuclear cross-section, and we'll talk about that later. But that's essentially what a nuclear table looks like, looking from close, right? And we still have, if you go to some professors' rooms, you'll find some of those hanging on the wall. We now use much more the ones on the internet because they are they are completely up to date and everything. But they are essentially the same thing, right? On the same line, you have all the isotopes for the same chemical element. And what are those nuclides? Well, if we think the ones that are theoretically stable, and we'll talk about this on the next class, we have 90. These 90 include all the first 40 elements. These, in theory, they should never decay. So we have 90 nuclides. Then we have some that, okay, if you do the math, you say, okay, this should be able to decay, but no one has ever observed that decay because they are much unlikely to happen. So this we define as stable. This is 162. So we have this 19 plus 162. We have 252 nuclides, which are what we defined as stable because we never saw any decay. Then we have the primordial radionuclides, which are essentially 34, which are bismuth, uranium, thorium, plutonium, which are radionuclides that are here from the time Earth was created, was assembled or something. Right, so we have 286 nuclides. You see it start to pile up quickly. Then we have the other natural radionuclides which can be produced By the decay of these they can be produced by reactions on the atmosphere and everything. It's 53 more. We come to 340, which are essentially the number of nuclides we find in nature. But we can produce nuclides in the lab too, right? The ones we can produce with half-lives larger than 1 hour are 556. So they are more than every nuclide you find in nature. And now we came to 900 radionuclides. But now if you look at the ones that we can do in the lab and have a half-life shorter than 1 hour, we have 2000 something. So the grand total of well-studied nuclides is around 3,300 nuclei, right? So you see we have a plethora of nuclides to choose from. And just talking about what is the nuclear interaction. Nuclear interaction we have, so as we said, we have protons and neutrons inside the nucleus, right? They can decay emitting beta particles, alpha particles. So we have electromagnetic force is trying to throw all this positive charge away, and neutrons are there to glue them because the nuclear force is attractive, right? If we compare the three interactions, right, it's in Portuguese, but the strong interaction that keeps the nucleus together, the intensity is 1, we normalize by it. Its range is very, very short. It's 10 to the minus 15 meters. You see, in fact, in a large nucleus, it's so short that one nuclide cannot see the other nuclide on the other side of the nucleus, right? Then we have the electromagnetic interaction, which is 137 times weaker than the strong one. The range of this is infinite, right? Then we have the weak interaction, which is responsible for some special cases of radioactive decay. We'll talk about this during the course. And its intensity is 1 million times smaller than the strong one. But its range is much, much shorter, meaning it only takes place inside the nucleon, not the nucleus itself. And finally we have gravitational force, which is much, much smaller, 39 orders of magnitude less intense, but its range is also infinite. It only takes place when we're talking about large masses, right? And 2 units we need to talk about here. The atomic mass unit, AMU, now it's called Dalton, right? It's 1/12 of the mass of carbon-12, right? And in this unit you have the electron weights something like 5 to the minus 4, meaning it's half a thousandth of the mass of the proton or the neutron. And the mass of the proton of the neutron, they are different only on the third digit. Another thing important, and the neutron is slightly heavier also, this is important. And the electron volt, as I told you, is the electron potential energy of one electron when it's under a 1 volt potential difference, right? So it's an energy unit. And that's what we had for today. Next class we'll talk about things like how can carbon-12 weigh 12 units when both the proton and the neutron are heavier than this? What consequences does it have, right? Because something strange is happening here. Yes, it is. That's what we'll talk next class, right? See you there.